great to have Rad Niazadeh here for our Research TTIC talk. Rad is faculty member at Booth and courtesy faculty here at TTIC. And we enjoy and appreciate all of Rad's interaction with us, and really delighted to hear what he's going to be talking about today. So,
thank you so much, Alvin. It's always a pleasure to give a talk at TTIC, because I don't need to pretend that I'm not myself. When I'm in business school, I kind of hide my TCS aspect, but when I'm in TTIC, I unleash that. And this is going to be actually one of the examples of that. So this talk is going to be about the recent paper, a Stationery online contention resolution scheme, which is a joint work with my PhD student, Mohammad Raza Aminian, and my postdoc, Pranav Nuti, both of which are sitting in the audience. So feel free to ask easy questions from me, and if you have any difficult questions, these guys are here to help. And this is a very recent work, so if you have any feedback, that would be absolutely welcome. So if you're here because you thought someone is coming from Booth to give a very application-oriented, flashy talk, I'm sorry that I'm going to disappoint you. This talk is going to be fairly technical. But at the same time, at some semi-philosophical layer, there is a message hidden in the talk, and that message is the following. So I hope I can convince you by the end of the talk that sometimes when you're looking at a problem and you're trying to find a solution, maybe by adding a structure, in particular symmetric structures to the set of solutions you're trying to find, the set of candidate solutions, you might be able to make the problem more tractable and actually find the suitable solutions. So hopefully in the context of online contention resolution scheme, whatever they mean, I can kind of convey this message. All right, so I'm not going to try that much to motivate online contention resolution scheme, but this is maybe the easiest way to motivate this primitive. So they're coming from the so-called Bayesian online optimization. There's a class of online optimization problems when an online algorithm has distribution knowledge about the future variables and is making decisions. And they have wide range of applications, from resource allocations to staffing problems to matching markets, names. So I'm not going to talk about these applications. Instead, what I'm going to show you is revisiting one powerful framework related to online optimization, the Bayesian online optimization, that will help you to design algorithms. And that primitive is what I'm calling online contention resolution scheme, or OCRS. All right? So let me explain a little bit. Many times when you want to solve a Bayesian online optimization, one strategy is the following. I have distribution knowledge about the future. I can use that distribution knowledge to set up some offline optimization problems. Maybe it is a linear program, maybe it's a convex program. It goes by different names in different communities. In algorithmic game theory, people call it ex-ante relaxation. If you go to OR, people call it fluid relaxation. So you solve these offline optimization problems, and that gives you a quote-unquote ex-ante plan. And then you can try to mimic this ex-ante plan. So one approach to mimic an ex-ante plan is online independent rounding. So I have some ideal probabilities for my allocation. I'm going to formalize everything. But just imagine I have some ideal probabilities for my allocation, and then there will be an online algorithm that rounds on a line from a vector x, which contains those probabilities. All right? So this is not going to be a real algorithm. This is going to be just some algorithm that independently rounds from the ex-ante plan, because probably it doesn't satisfy the constraints of your problem. Right? So let me try to formalize this in a particular context. So imagine this algorithm is eventually trying to pick a subset. Let's say I have n different elements, and then I'm going to define a family of subsets of 0, 1 to the family of subsets of this ground set. Let's call it F. Imagine this is a downward closed family, meaning that if a set is feasible, then everything that is a subset of that set is going to also be feasible. I'm also going to define the convex hull of the incidence vectors of all the feasible sets. Let's use the notation P. So suppose I give you a vector x. This is kind of like representing my ex-ante plan that belongs to the convex hull. And this P is known by the online algorithm. It's kind of given to the online algorithm. And then this sampler, this independent rounder, is just going to start with x. And as the input arrives, it's going to independently round elements of x one by one. So basically, each element E is going to be independently given to the algorithm. Essentially, it's active with probability XE. Right? Now, the goal of the online algorithm is to basically observe this element as they arrive, observe their activation state, whether it is active or inactive. And then if the element is active, the online algorithm has a decision to make, whether to accept or reject. If it is inactive, the online algorithm should pass and go to the next element. But if it's active, it might accept or reject that element. So the goal of the actual online algorithm, in contrast to this independent rounder, is to have a pointwise feasible set. So basically, the online algorithm should select the set S that belongs to the family of feasible sets F. Right? And at the same time, the online algorithm wants to be as close as possible to the exante plan. In particular, you kind of want to create some tool, I'm going to call it online contention resolution scheme, I'm going to formalize that soon, when revisits this exante rule, the activation is generated by the online rounder, and then makes these decisions accept, reject, so that you only lose maybe alpha factor in terms of the allocation, final allocation probabilities. And if you manage to do that, then going back, circling back to the Bayesian online allocation, you will have actually an algorithm that can solve your Bayesian online optimization problem up to some multiplicative factor alpha. Right? So let me try to first make sure that you understand the difference between exante feasibility and ex-post feasibility. So every time that in the talk I say exante feasibility, I'm referring to the fact that you have a fractional vector x that belongs to the polytope. And then the ex-post feasibility refers to basically an online algorithm that at every single time should pick a subset that is feasible. Like for example, let's say this downward closed feasibility set is a set of all the matchings in a graph. Then being exante feasible, meaning that I have a fractional matching, something that is in the matching polytope. And then being ex-post feasible, that you have an actual matching when no vertex is being used twice. So now, if the online rounder, say, gives me the edges of the graph, and once an edge arrives, you get to see the activation and activation. If I select all the active edges, in this case, edges that are blue, then you have the maximum selectivity. Alpha is going to be equal to 1, meaning that you're going to be exactly same as the exante plan in terms of allocation probability of the edges. But then this is not going to be matching. This is just going to be matching in expectation, meaning that if I look at any vertex in the graph, the expected number of the edges that are incident to that vertex would be at most 1. Right? And this is what an online contention resolution would do. So the basic primitive of the problem, you have a ground set E together with a downward closed family of feasible sets F. You look at the convex hull P, and let's say the online algorithm is endowed with a fractional vector x that belongs to P. This is basically the example plan. Now, elements belong to a set of active elements, A, independently. So basically, every element independently of probability XE belongs to the set of active elements A. And now, imagine this set in an adversarial order pi will be presented to the online algorithm. For the purpose of this talk, maybe it is easier to assume that the online algorithm actually knows the order pi, but soon you will see that I actually don't need that assumption in most of the technologies I'm going to create in this talk. Yes?
So actually, maybe just backing up to the definition of the problem on one slide before this.
Yes.
Just trying to get an understanding. So if script F looked like either the first third can be 1, the middle third can be 1, or the last third can be 1, or any downward parts.
Yeah, like boundary from each side.
Then the fractional solution might have everybody at 1/3.
Correct.
And then if we did this online, what would happen is, like, I don't know, the first thing it's a 1 would kind of force you now to, like, you
selected with probability at least.
So alpha would have to then be at most 1/3 then, or so. In other words, you'd have to throw out 2/3 of the things, right?
Yeah, so this is basically, so you want to make sure that you're close to the exante plan, meaning that your allocation probability is alpha times that 1/3. So basic condition, the element being active, you want to make sure that you've selected with probability alpha. But then the unconditional selection probability would scale with the exante plan. So if you give me an exante plan that is like 1/3, 1/3, 1/3, then I might be able to get, like, say, half of that 1/3, and that's fine.
It seems like doing it this way,
yeah,
it'd be even worse because you're like if they're coming in one at a time, they're each one with probably a third. But you're going to have to, if they're in some random order, you're going to have to throw out 2/3 of them, all the ones that weren't. It feels like you're only going to be able to keep 1/3 of the ones you actually want to keep, so that the alpha would. Like I couldn't see how you. It seems like there's no way to get a constant alpha here.
Yeah, I mean, just imagine that. Let's say you have let's say you have 3 elements. Each one is going to be active probably 1/3, and a set of active elements is just singletons, right? So if I don't pick the element probably half, then when I get to any element, there is a probability half that I haven't selected anything using union bound. And then condition that element being active, you're going to select it down the probability half, so that gives you alpha equal to 1/4. So maybe
you always get a constant factor alpha for arbitrary f's?
No, that's not true. Okay. So there are, I think the one that you're mentioning is more like set cover for those who can't get constant, but there are certain distributed environments for which you can get constant. The alpha doesn't need to be constant all the time. It's like the best thing you can get.
Okay.
All right. So, right. So the online algorithm observes this activation bits and should make selections. At the end of the day, the online algorithm should pick a set that is subset of the active elements, and it should also be feasible. But maybe more important than that, you want to make sure that each element is going to be covered enough. So conditional element being active, you want to select the probability alpha, or the unconditional probability of selection of every element E in this randomized scheme should be at least alpha times X. All right, so let's demonstrate that. Element E1 arrives, you observe the activation bit. You might want to accept. E2 arrives, you observe the activation bit. This one is also active. You might want to reject, maybe to maintain feasibility. E3 arrives, you observe the activation. Let's say I accept this one. E4 arrives. This one is inactive, so you have to reject. You never accept elements that are inactive. And that can be like one trajectory path of an online contention distribution scheme. And there are many ways that one can design these algorithms. So there is one way that will be relevant later in the talk. I call the distributional view, which basically characterizes the search over these online algorithms that maximize the selectivity alpha to a linear program over the space of distributions. Basically, rather than trying to find the algorithm, I try to search for the final joint distribution of allocations of the elements, and I try to find one that can be implemented by an online algorithm. So this will be some LP. So let's try to understand this LP. I'm trying to maximize alpha, the selectivity, subject to essentially 2 constraints. So the first constraint says that whatever joint distribution you have should contain every element with probability at least alpha times xe, so that your scheme is alpha selectable. And then the second constraint is kind of interesting. I call that online implementability, so meaning that you have some joint distribution for every E and for every feasible prefix T. Imagine some points during the execution of the algorithm. So the probability that you select an element, conditioned on whatever you have selected so far, should be no more than the total probability that the element is active. Because at the end of the day, you always pick active elements. Right? So let's add that constraint to the LP. So this seems to be necessary, because if you have any online contention resolution scheme, you only pick active elements, so therefore the conditional probability should be no more than the probability that the element is active. So I claim this is actually sufficient. So in fact, you give me any feasible solution to this LP, I can round it exactly without any loss to an online algorithm that is alpha selectable. And here is what I'm going to do. So there's this algorithm, I call it sample then append, STA, and it does the following. So at the start, at the outset, you have the empty set, you haven't selected anything. Now, let's say elements arrive one by one. So for example, E1 arrives. Then here's the algorithm. It's very simple. What I'm going to do, given a feasible solution mu superscript x pi from the previous LP, I'm going to compute this quantity QET, which is basically the conditional probability that E is selected in that joint distribution, conditional on the particular prefix. In this case, at the beginning, it's going to be empty set. And if the element is active, I'm going to select it with probability QET divided by XE. And this ratio is always between 0 and 1 because of the feasibility of mu. Right? And let's do that. So I'm going to basically sample, somehow basically select E1 and add it to the T. And I claim this is the equivalent of the following process. Let's say you want to create a set S from mu at the end. So you can actually sample elements one by one, right? So you can sample E1 from the marginal distribution, then you can sample E2 from the conditional distribution, and then you can sample E3. And this is exactly what this algorithm does. So basically, once you get to the end, you get exactly mu. And not only that, at every step throughout the process, the prefix law, the joint distribution of the prefix that you have created, is going to be exactly the joint distribution of the prefix generated by, say, mu. Right? So all I showed you is that the search over algorithms can be reduced to a search over distributions. In particular, solving an LP when the decision variables are the distributions over physical sets. Okay? So hold on to that thought. We're going to build on that. But before getting there, so I'm not the first person who has studied online contention resolution schemes. This has been studied in TCS literature. In fact, in the context of submodular optimization, people studied the offline version of contention resolution. I don't have those papers on this slide. And that, later on, when people think about online Bayesian online optimization, created online contention resolution line of work. It started with the work of Feldman, Svensson, Zen-Coulson back in 2016. And since then, people have studied various feasibility environments. Like, for example, we have in the literature, there are so many examples of papers looking at the K-uniform matrix, the K-selection problem. When I give you n elements, and the physical sets are going to be those whose coordinate is no more than K. You can think about, say, general or bipartite matching, when the feasible sets are going to be edges of a graph, and maybe a bipartite graph or a general graph that form a matching. There are also, almost any feasibility environment that I can think of has been studied. One last one, which is related to this talk, matroids have been studied. And in particular, in the context of profit inequality for the experts in the audience, we know profit inequalities that are half approximation versus the example relaxation, and then there are these dualities between the contention resolution, online contention resolution, and profit inequality versus example benchmark. Through those, you have some implicit algorithms that are half selective online contention resolutions for general matrix. Kind of like the picture, and I'm projecting this huge line of work into whatever is relevant to a talk. There are many other papers, many other feasibility environments that researchers have studied. All right? So one observation, if you look at these papers and also other papers, is that many times there is a shortcoming in this line of work. In particular, the constructions that you often find are sometimes suboptimal. Sometimes they're optimal, but also sometimes they're suboptimal. They're very environment specific. There are so many delicate, complicated algorithms in this literature, and their designs are very ad hoc. And sometimes, like for example, for the general matroids, even there is no explicit algorithm. It's kind of like an existence result through a duality argument. All right? So therefore, the main question I'm going to ask in this talk is the following. Is there a principled approach to design online contention resolution schemes? And in particular, I'm wondering if there exists some almost problem-independent framework where you can kind of like set up this problem in a way that is not related to the particular feasibility environment you want to study. And then through that, you try to design online contention resolution schemes, and hopefully this framework can be applied to many feasibility environments. Second question is that many times, not many times, but sometimes there are implicit algorithms in the literature. Can I design concrete descriptive algorithms, basically those with explicit constructions through this framework? And finally, kind of circling back to the semi-philosophical point I had at the beginning, can I add some structure to this problem? In particular, some symmetric structure, so that through that I can actually design simpler algorithms compared to the ones that exist in the literature. Right? So these are very high level. I'm hoping I can make it more concrete. So any questions up to this point? You guys just feel free to stop me at any point.
Another question. So just trying to understand. So the class of algorithms, they solve for a fractional solution. And at that point, though, that's kind of it. Everything else.
So the fractional solution is given to the online contention resolution scheme. Imagine there was an LP that you solve.
Okay.
Like an example, something very simple. Like for say, allocation problem, when the example that we mentioned, you want to maximize maybe the expected values that some of the expected values that you can get from n different buyers, subject to the constraint that only one of them gets the item in expectation.
Okay.
So you can solve that problem up front. That will give you the right allocation property for each buyer. So that's vector x. And that's given to the online algorithm. Now, there's an online rounder that rounds that example plan and creates its activation list. So in the context of pricing, for example, that corresponds to I'm setting prices to these buyers that are arriving. When the total probability of a buyer accepting the price is at most 1.
So what the algorithm then gets to do, good, so after that, gets to decide how it wants to do the rounding. Yes. The order is given. The algorithm doesn't get to pick the order. That's given.
Yes, and let's say the order is given, but in fact, in most of the literature, the order is not only adversarial, but it's also unknown to the algorithm. And in fact, soon when I talk about the stationary online contention resolutions, I'm going to...
So it's just a question of, I have this fraction now, I need to round it. Yeah. And you don't... The algorithm does not, like you could imagine partway through saying, you know what, let me actually resolve the fractional given the decision so far, and we don't do that.
No, x is fixed throughout.
Okay, thanks.
Just to make sure I understand correctly, the algorithm is given both x and pi, right?
For now, let's assume both x and pi are given to the algorithm. Like for example, in my distributional viewpoint, for the online contention resolution, in order to write down the LP, you actually needed to know the order. So let's, for now, I think that pi is also here. But I'm going to drop that assumption.
Okay, good.
All right, cool. So this is a new principle that I'm going to add to the problem. So I'm going to look at a set of restricted online contention resolution schemes that are order invariant, meaning that the joint distribution that they have over the allocations is not going to be a function of the order pi. And because of that, I can just imagine that I don't know the order. So imagine there are 4 elements, A, B, C, D. They might arrive in the order A, B, C, D, or they might arrive in the order D, B, A, C, 2 permutations pi and pi prime. So regardless of which one you pick, the algorithm should give you the same joint distribution over the subset of A, B, C, D that is selected. Let's say I add this restriction to my algorithm. And I claim that, well, so I think this symmetry is restrictive, but this created structure will help you to design better algorithms. So let's see why. So first, I'm going to define this restricted class. I'm going to call them a stationary online contention resolution schemes. I'm going to use the abbreviation S-OCRS for these new algorithms. Formally speaking, regardless of the ordering pi, the joint distribution mu superscript pi and x should not be a function pi. So mu superscript pi and x should be the same as the mu superscript pi prime and x. And when you think about this, basically when order matters, somehow the algorithm is keeping track of the joint distribution of the prefixes, but then order doesn't matter. Really, like this algorithm should care about one single distribution, like the joint law of the selections that will kind of be the same throughout. Let me try to explain. So in fact, the previous distributional viewpoint has an analog, which is a distributional viewpoint for designing a stationary online contention resolution scheme. So this LP is going to be a restriction to the previous LP. Everything is almost the same, except the online implementarity constraint. I'm going to change it to what I call a stationary implementarity constraint. So what is this new constraint? So for every element E, and for every set T, which is feasible, and think of T as the remaining element except E, the probability that E is selected, condition on the remaining is equal to T, should be no more than XE. All right? And I think this is coming from somehow the viewpoint that if you have an algorithm that is order invariant, pick any element E, we can just imagine this element is coming at the end. And in order to be able to select that, similar to the way that we think about online contention resolution schemes, something like this should be true. So this is definitely a necessary condition for a stationary online contention resolution scheme. And similar to the other distributional viewpoint, I claim this is sufficient. In fact, there is an algorithm that can losslessly round any feasible solution of this LP. I'm going to call it now sample then replace, abbreviated as STR, and this is what the algorithm does. At the outcast, actually sample a set S hat from the distribution mu, the feasible solution of the LP that you started with. Imagine this is kind of like some imaginary state of the system. Now, every time an element E arrives, first thing I'm going to do is that I'm going to erase that coordinate corresponding to E. Regardless of whether it is 0 or 1, I'm just going to erase that coordinate. And then here's what I'm going to do. If the element is active, I'm going to select it with probability QET divided by XE, when QET this time is the probability that E is selected, condition on the rest is equal to the T when T is the basic S hat minus E. All right? And if the element is accepted, I'm going to add it to S hat, add it back to S hat. So I claim this is not actually changing the distribution of S hat. Basically, this is kind of like resampling. So you have some set S hat. Let's say you pick some element E1. Then you can drop that element and then resample it from the correct conditional distribution. And if you do that, the new S would have the same distribution. So if I basically continue this process, at every single point throughout the process, the distribution of the new S hat would remain the same. And this is why we call these things a stationary and contention resolution. Let me try to give you a pictorial proof, not a proof, like some picture that will help you to understand the proof, and then I'm going to give you a very simple inductive proof for this fact. I already said that in words, but let me try to formulate it. So this is the picture you want to have in mind. So you start from some S hat and at the beginning, and then you try to resample over time. So you always remain in the same distribution, but then if I stop the process at some point, when, for example, you finish processing the ith element, then there is a prefix and then there is an imaginary state. So the prefix are the actual allocations you have made up to that point, and then the rest is just some imaginary states. These are not the allocations you have made, but in distribution, they are kind of like the allocations you would like to make. All right? So let's, is this picture clear, like what is happening? So you start from some set S hat, and then you keep resampling, you couple them with your actual allocations, and then once I finish, everything is going to be my allocation, and you will be at the same distribution. So the proof is simple. It's basically induction. At the beginning, of course, S hat is from distribution mu. Now, every time a new element arrives, the probability that E is my S hat mu. So if you look at S hat mu, everything except E is exactly the same. I'm just resampling one element. So now the probability that E is in S hat mu condition the remaining coordinates of S hat mu, which is the same coordinate as S hat, would be the probability that it is accepted, it is active, times the probability that it is accepted, which is XE times QET divided by XE. So this is going to be exactly QET, which is the correct conditional probability that you should have sampled. So everything else is the same. This element is resampled from the correct distribution, so therefore S hat mu will have the same distribution mu super TTIC. Any questions about this proof? Very simple, but kind of at the core of the talk. All right. I reduced the problem of designing a stationary and contention resolution to solving the previous LP. Basically, if you give an environment, I'm going to find the distribution mu x, which is a feasible solution to the LP for a given alpha. And if I do that, I have an algorithm that will be alpha selected, and that's just the sample then replaced. So in some sense, this problem is reduced to solving that LP. Right? And let's see actually how we can solve that LP. And this is the point that I should convince you, adding this symmetry is helpful. Because this is just a more restricted problem, right? It's not, it's a little bit counterintuitive that if you look at the restricted version of the problem, it becomes easier. But it will be. And this is the one funny connection. So let's think about what distributions would be actually easy to work with. And here is one example. Let's try to solve a maximum entropy convex program over the space of distribution. In particular, I'm trying to kind of like fix some target marginals for the selections. Let's say the original vector you started is x. I'm gonna target a marginal p, which is equal to alpha times x, and alpha is the target factor that you want to get at the end. And now, let's write down a simple convex program where you're maximizing the entropy of this distribution over physical sets, subject to the constraint that your selection probability is exactly equal to p. So that gives you some distribution of physical sets. And in fact, two things. This convex program can be solved in polynomial time if you have access to an approximate counting oracle for that feasibility environment. So in many feasibility environments I'm going to play with, we have that. So you can imagine I can solve this in polynomial time. That's something that needs to be figured out. But for, say, matchings or the class of weakly Rayleigh matroids, these are the names that you're going to see soon, you can actually solve these convex programs. That's the first observation. The second observation is that whatever distribution you get will give you the coverage. Why? By construction, because you ensure that each element is going to be selected with probability alpha times x. And then the third observation is that this distribution is going to be a so-called Gibbs law, meaning that there is a vector W1 to WE, a weight vector, and the mass that you put on every set S would be proportional to the product of the WEs. And in fact, these WEs are equal to some e to the power theta e's, and these theta e's are related to the dual of the convex program. Right, let me try to prove this property quickly using essentially the KKT conditions of the convex program. So you want to solve the convex program. Let's write down the Lagrangian. I'm trying to maximize the entropy, so this comes in the objective. There's one constraint corresponding to the marginal inclusion probability for every element. I'm going to introduce the dual variable theta e for those. There is one constraint for the distribution to be in the simplex. Let's use the dual variable gamma for that. If I write down the KKT condition, the first one is the stationary condition, the first order condition, the gradient of the Lagrangian with respect to mu should be 0. You set it to 0, and this is basically telling you that in the optimal solution, the mass that you should put on every set S should be proportional to the product of WE's, when WE's is e to the power theta e for the optimal dual variable theta e. And here, if alpha is between 0 and 1, if you're concerned, you will be in the relative interior of the feasible set. And because of that, you can apply a later condition, and therefore, there is a unique optimal solution. Not only a strong duality holds, but also there is a unique optimal solution for this convex program. Right? So, all I have done so far is that I created a distribution with the correct marginals that is a Gibbs law, and that's it. And let's see why this Gibbs thing is kind of like helpful for designing S-OCRs. I'm going to claim that the problem after, so the only thing you need to check so that you have a stationary OCRS algorithm is whether this distribution satisfies the stationary implementability constraint in the LP. Remember, so if that constraint is satisfied, there was this lossless rounding, the sample then replaced. But who said this is actually a stationary feasible solution, satisfying the stationary implementability? I need to check that. So let's try to check that. I need to compute the probability that an element is in my set S when S is sampled from some Gibbs distribution, condition on, say, the remaining elements is equal to T. Now, this is the part that Gibbs will help you. So this calculation, so if you're trying to find this conditional probability, this is now equal to the probability that S is equal to T union E divided by the probability that, so if S minus E is equal to T, then S is either T or T union E. So therefore, the sum of the probability that you have a T or you have T union E. And if these are Gibbs, there will be a lot of cancellations. In fact, the only thing that is left would be WE divided by 1 plus WE if T union E is feasible, and otherwise it's going to be 0. So let's define a notation. Rho E would be WE divided by 1 plus WE. Then this is basically what I proved. This conditional probability that I need to check is always equal to WE divided by W plus 1, essentially rho E, times the indicator that T union E is feasible. And now what you need to check is that whether this is at most XE, right? So if it is at most XE, this is going to be a stationary implementable. In cases this is infeasible, this is 0, so it is at most xe, trivially. So all I need to show is rho e is at most xe. Or in other words, I need to kind of like find my alpha property so that rho e is at most xe. Let me do one more calculation, which is now making the problem even easier. I'm going to define this event called addability. So add e is going to be a 1. If basically, imagine S is sample from my distribution. If I remove e and I add it back, it's going to be feasible. It's kind of like, basically you can add e to S minus e. Let's call that event addability. And the previous slides, I just like have different notation, showed that the probability that e is selected, condition on S minus e is equal to t, is basically rho e indicator that addability happens. Now, let's take an expectation from both hand sides. So the left-hand side, by law of iterative expectations, will become the marginal inclusion probability that e is in S, which we already know is equal to alpha times xe. And then the right-hand side becomes rho e times the probability of the addability. Meaning that if I sample S from my distribution, I remove E, can I add back E? What is the probability of that event? Right? So you need to show that rho is at most alpha. Sorry, you need to show that rho is at most xe. So for rho e to be at most xe, going back all the way to the left side, all you need to show is that the probability of addability is at least alpha. So if you can show probability of addability is at least alpha, then you have actually an alpha selectable stationary only contention resolution. Is this calculation clear? So let me kind of like give you a summary of what happens. You start from some environment. Your goal is to design, say, an online contention resolution scheme, or maybe an stationary online contention resolution scheme. The first step is you target certain marginal vector p, which is equal to alpha times x. Then we know that once we solve the max-entropy convex program, it's going to give us a Gibbs law that satisfies that marginal distribution, the target marginal. But we don't know whether this is a stationary. And all I showed you that in order to show this is a stationary, you need to check whether the probability of add e under that distribution, under that Gibbs distribution, is at least alpha. Right? So this is the recipe that I promised. If I can show that probability of addability is alpha, then I have an alpha selectable S-OCRS, which is, of course, an OCRS. Right. So maybe I could end the talk at this point, but it wasn't convincing. So in order to make it convincing, what I'm going to do is I'm going to actually go over a bunch of applications. I'm going to show you how we can get very simple S-OCRS algorithms and therefore OCRS algorithms for these particular applications. So I'm going to start with matchings. I'm going to switch to K-uniform matroid, and if time permits, I'm going to tell you a little bit about this special class of matroids called Vickrey-Rayleigh matroids that contain things such as linear matroids over complex numbers, which includes graphic matroid and laminar matroids, and therefore K-uniform matroids. All right? So matchings. There was a paper by Ezra et al. For experts in the audience that accumulated profiting quite. That was actually a very beautiful paper that showed how we can get a 1/3 OCRS for general matching. And that actually an entire paper. Let me show you like a 2-liner proof that why with my framework you can actually get a 1/3 OCRS, in fact S-OCRS for general matching. So all you need to check is whether the probability of addability is at least 1/3. Right? Okay, so I'm thinking about general matching. So feasible cells are going to be matchings in a graph. I have a distribution, in particular Gibbs distribution over the feasible matchings. And then we are focusing on one particular edge E, and we're asking what is the probability that if I remove E and I sample a matching from that distribution, I can add back E and still I will have a matching. I mean, this is basically equivalent of saying that, well, under S hat minus E, none of the endpoints should be matched, right? So if I show that under S hat, what is the probability that none of the endpoints is matched, then I'm also good to go. Like that's going to be also a lower bound on the addability. So let's do that. And I'm just going to use union bound. So if I think about my S hat that has marginals alpha times xe, and xe is a feasible point in the matching polytope, what is the probability that U is being matched, is occupied? It's going to be at most the probability that one of these edges incident to U is selected. So that's going to be alpha times the summation of xf for all the f's that are in the neighborhood of the vertex. And because x is the feasible point in the polytope, that's going to be at most 1. So the probability that any vertex is selected is at most 1/3. So the probability that either U is selected or V is selected using another union bound would be at most 2/3. So the probability that none of them is selected is at least 1/3. So therefore, probability of adability is going to be at least 1/3. And that essentially tells you using sample then replace, if you solve the max entropy convex optimization over the space of matchings, when alpha is equal to 1/3, you can have a 1/3 stationary on contention resolution scheme. That's it. Let's switch to bipartite graphs. I'm going to show you that there exists a stationary O-CRS that obtains a factor alpha star equal to 3 minus the square root of 5 divided by 2. It's like 2 plus golden ratio. It has some connection. 2 minus. 2 minus. Thank you. And this factor was conjectured for a while. This is achievable for bipartite graphs. It was shown that this factor is achievable when you have a vanishing instance of the contention resolution problem and the probabilities are small. And it was conjectured to be the best bound that can be achieved by any online contention resolution algorithms. And in fact, it is proved to be the best bound achieved by a very, very natural class of online contention resolution algorithms for bipartite matching, but it wasn't known whether you can actually get this bound. And here is a very simple O-CRS, and in fact S-OCRS that achieves this bound. And this is going to be an optimal S-OCRS. We have a lower bound in the paper that shows this is the best factor you can get. So, again, the same thing as before. All I want to show in the same setting, the only difference is that graph is bipartite, is that the probability that none of the endpoints is matched is at least 1 minus, none of the endpoints is matched is at least alpha star. That's what I'm going to show. All right? And this is something now I'm going to use the fact that I have a Gibbs distribution a little bit more. There is a lemma that we use in the paper for certain people that in TCS and in math, they think about sampling and counting. This might be considered as a standard lemma. Maybe even for statistical physicians, this might be considered as a standard lemma, known as Hillman-Lieb or monomer-dimer property of the Gibbs distribution over bipartite matching. So basically, it says that the event that U and U is selected, basically reactants that are selected are negatively correlated, and the event that they are not selected by the matching are positively correlated. Basically, the probability that U is unmatched and V is unmatched because of the positive correlation is at least the probability that U is unmatched times the probability that V is unmatched. I'm going to use this lemma. We actually have a proof in the paper. It's a pretty combinatorial, nice proof, but I think this is Pranav consistently called this a standard lemma. So, I'm going to refer to him why this is a standard. It's well a standard to me. All right. So the rest of the proof is exactly as before. So the probability that something is occupied is at most alpha. The probability that something is not occupied is going to be at least 1 minus alpha. Now, using the positive correlation, the probability that neither U is occupied nor V is occupied would be at least 1 minus alpha squared. And now my alpha can be as low as 1 minus alpha squared. So if I set alpha equal to 1 minus alpha squared, that's going to be the 3 minus the square root of 5 over 2. And I just showed you that basically, again, if you solve the convex program over the bipartite matching, then the target marginal you're trying to get is alpha star times x. Will give you a distribution. It can be computed in polynomial time, trust me, using basically the fact that there is an approximate counting of bipartite matchings. And then the sample then replace algorithm will be the one that gets this factor. All right. Any questions? So this is basically the best S-OCRS algorithm. And I said this in words, so this is kind of like achieving the quote-unquote independence benchmark, which is conjectured to be the best bound for bipartite matching on a contention resolution problem. You had a question?
Yes, like for the matching, so the first step of the algorithm is to sample from the monomer dimer. Is that right? And then that's not always known to be tractable, is that right? Or
For bipartite matching, you can actually compute that.
but for the general one, it's
No, right.
Well, approximately sample.
You can approximately sample. You cannot exactly sample for general one. You can approximately sample.
Even for bipartite, you might have to approximate.
Yes, it has, basically it uses the matrix tree theorem because that gives you like exact counting, and then if you're counting with weights, then you can actually use that. So there is a reduction between sampling and counting, and this can be using it. All right. A matchmaking entry. All right. So let's switch to the second application, K-uniform matroid. It's a very simple set system. You have a ground set of n elements. The feasible sets are going to be those that their coordinate is bounded by k. You start with the vector x that is in the polytope, meaning that summation of x is at most k. And now an online algorithm gets to see elements one by one, observe the activation, should select at most k of them, and should guarantee that condition an element E being active is being selected with probability alpha. And here, maybe it's even like more clear for people in OR. So somehow k is the size of the market. So if k gets large, you should expect to be able to get a 1 approximation. In fact, a very simple coin flip algorithm, so let's say every time we see an element, like the extension of the algorithm I told you, Avrin. So if I flip a coin with probability of discarding equal to a square root of log k over k, right? Then every time I see an element, you can use Chernoff bound to say, with high probability you haven't selected anything. So that coin flip algorithm will give you a selectivity of 1 minus order 1 over a square root of 1 minus order a square root of log k over k. So getting log k over k is trivial. But then there's this beautiful paper by Saeed Alaei back in 2014. There's this algorithm called the magician's algorithm that obtains the factor 1 minus order 1 over a square root of k, which is information theoretically optimal. And later there was some follow-up work that using factor revealing LP and duality, they show that that algorithm is actually the optimal algorithm and then identify the more refined bound, which is in the order of the same thing. But this is actually a very complicated algorithm. I'm teaching this course on online optimization, and I have taught it, I think, 5 times now. Every time I'm asking myself, should I teach the magician's algorithm? And the answer keeps being no, because this is not something teachable. You can't cover that in even like a 2-hour class. The algorithm itself is complicated, it's very counterintuitive. Maybe for Mohammad Reza it is not counterintuitive, but it was counterintuitive for me when I read the paper for the first time, and even the analysis is even worse. It's a beautiful analysis, but it is complicated. And then there are like 2 OR papers that they try to analyze that same algorithm to show this factor and maybe refine bound. So it's not an easy peasy task. But I'm going to show you that you can get these using an almost trivial Gibbs distribution. Consider the following Gibbs distribution. I'm going to sample every element with probability gamma times xe, called rho e to gamma times xe, for a gamma that should be determined soon. Gamma is going to be 1 minus square root of 1 over 2, order 1 over 2. So sample an independent set with probability, when every element belongs to the independent set with probability rho e equal to gamma times xe, and then use rejection sampling to condition the event that the size of the set is at most k. So that will define the Gibbs distribution when the parameters are basically with the weights are WE, which is equal to rho e divided by 1 minus rho e, because the probability that you have a set S would be proportional to the product of rho e is E in S times the product of 1 minus rho e not in S. So if you divide by the product of all the 1 minus rho e's, then the WE would be equal to rho e divided by 1 minus rho e. And it's a Gibbs distribution. Right? Now, what I'm going to do is I'm going to use that Gibbs distribution, and run the sample then replace algorithm using that particular Gibbs distribution. And then here's one immediate observation. Rho e, which would be that same conditional that I always use, is equal to gamma times xe for some gamma that is between 0 and 1. So this distribution is going to be a stationary. It satisfies the stationary implementability by construction. The thing that it might not satisfy is the coverage. Maybe I don't get enough coverage. Let's see if that is the case. So I'm going to show you that this very simple Gibbs distribution will give you actually coverage of 1 minus the square root of 2 over k up to lower order terms, which is optimal. And the proof is quite simple, so let me actually go over that. So what I'm going to do is the following. So I'm going to, let me define a bunch of random numbers. So ye would be Bernoulli independently probability gamma xe. Think of n as the number of ones that you get in this Bernoulli trial. And then mu would be the distribution that we talked about, which is basically the distribution of the ye's condition, the events that their summation is less than or equal to k, right? So coverage, the probability that E is in S, that's going to be equal to the probability that ye is equal to 1, condition on n being less than or equal than k. And that's basically the probability, well, first of all, you need to have room to accept, and you also need to accept, right? So gamma x is the probability that you're going to accept, and you can accept if basically n minus e is less than or equal than k minus 1, or say n is strictly less than k as a lower bound. But you should condition on the event that n is less than or equal than k, because that was your correct distribution, right? So this is basically a lower bound on the coverage probability. And n is a very friendly random variable. It is a Poisson binomial random variable. It's the sum of a bunch of independent Bernoullis with different properties. So probably I have actually some good control over this quantity. And that's actually the case. So first of all, let me replace this with 1 minus probability that n is equal to k divided by the probability that n is less than or equal than k. I'm going to show you this probability is going to be upper bounded by order 1 over root k, and then I'm done. So here's the simple proof for that. Well, so one observation was n. Maybe that can be one takeaway of my talk. If you're not familiar with some of the Bernoulli trials with different probabilities, it's called Poisson binomial distribution. Similar to the binomial distribution itself, it has all these nice properties. In particular, it is a unimodal distribution when mode and median are within one distance from the mean itself. All right. So now I'm going to define gamma to be 1 minus the ceiling of k, the square root of 2 over k. And because of that, gamma times k, which is equal to k minus r, will be some integer. And then expectation of n is gamma times the summation of xe, which is at most gamma times k. So gamma times k is an integer that is greater or equal than the mean. So it should be after the mode and median. That's all I'm going to use. Okay? And then, probability that n is less than or equal than the k, the denominator in the ratio I want to bound, we can write it down as the probability that n is between gamma k, and plus the probability that n is less than or equal than gamma k. So gamma k is like a point after median, so this probability is going to be at least half, and therefore it's going to be greater or equal than this other probability. So this is at least 2 times the probability that is n is between k and gamma k. And this probability is just equal to the summation when I'm adding up the probabilities from gamma k plus 1 to k. And this is a unimodal distribution. I'm going to use now the fact that it's unimodal. So the PDF is going to be decreasing after the mode. So therefore, this summation is going to be at least the number of the terms, which is r, times the probability of the last term, which is n equal to k. And if you rearrange the terms, all I showed is that the probability that n is equal to k divided by the probability that n is less than or equal than k is actually at least is at most 1 over 2r. And therefore, the probability of selection, the final one, is going to be at least gamma, which is 1 minus r over k, times 1 minus 1 over 2r, and that's 1 minus the square root of 2 over k. And that's it. So this scheme is going to give you an asymptotically optimal unknown contention resolution scheme for K-uniform matroid. And if you're trying to, you can try to optimize a constant, and then you can use the max entropy machinery. So if you use the max entropy machinery, then you can actually get this factor. I'm going to call it the Poisson factor, which is 1 minus the square root of 2 over pi k. This is basically the probability that Poisson random variable with mean k is less than k divided by the probability that the Poisson is less than or equal to k. All right. So in the interest of time, I can show you the proof. So for dips coming from max entropy, all you need to show is that probability of addability is at least whatever that you want to show. And in this case, basically, the t, which is, well, so still you're going to have a Poisson binomial distribution, and now this time rho e's are going to be what you get from the convex program. It turns out that expectation of t condition t less than k is at most alpha k times k because of just the feasibility expectation. Now I can compare that Poisson binomial with a Poisson, that's essentially the proof, and then that gives you alpha. So let me not tell you more. This is a little bit too much. It's a simple proof similar to the other one. Okay, so just maybe 1 minute. This approach is not going to work for general matrix. And the bad example is this example called the hat instance, where it basically shows that if you pick maximally spread distributions, then you're going to put so much mass on bad configurations. For example, in this case, hats of length 2 that block U to V. This is graphic matrix. So the independent sets are the feasible sets, which are farthest in the graph. And therefore, you can't pick this edge with enough probability. In fact, there is no constant competitive or constant selectivity algorithm using the max entropy. Just like a simple counting argument, which I don't have time for. But then it turned out that there is a revised version of our template, which only works for a subclass of matrix, a weakly Rayleigh matrix. I'm not going to tell you exact definition. We get a paper for the details. And this revised template essentially starts from selecting a base using the modified version of max entropy. I'm minimizing the KL divergence with some base distribution which exists for weakly Rayleigh matrix, subject to the correct, in fact, a slightly higher target marginal vector. And then there will be some thinning after that. But there are so many details, but at the end of the day, this is a very mechanical modification to the previous approach. And that will give you half for weakly Rayleigh matrix. And half is the best you can hope for, even as online contention resolutions. All right, let me try to wrap up. In this talk, I talked about how we can design these online contention resolution schemes. As I mentioned, they have applications in Bayesian online allocation. So I hope I could convince you by adding symmetry, the problem becomes more tractable. I was texting Jason Hartline this morning telling him that he should come to my talk if he wants to see some connection between profit inequalities and max entropy distribution. So I think I showed you some connection between profit inequalities and max entropy distribution, which to me was kind of cool. There are so many open problems. Every time I give a talk at TTIC, I try to have a list of open problems. So is there a half-selectable association online contention resolution scheme for general matrix? That's one question. Well, if we switch to general matching, I showed you 1/3, but actually we don't know what is the best association online contention resolution scheme we can design. So it seems using our approach, we can get 1/3, and maybe you can get this square root 3 minus 1 over 2, but none of this is actually the optimal factor for general matching. I leave that as an open problem. We can think about extending this approach to other feasibility environments. There are more feasibility environments in our paper I haven't discussed, but I'm sure that there will be other feasibility environments that even we haven't studied, we haven't considered, and this approach might be helpful there. And then another question, maybe interesting for TCS-minded folks, can you characterize the gap between a stationary online contention resolution and online contention resolution? What is the price of a stationary? Can you actually find how bad list we can get. In certain environments, there is no gap. In some other environments, we actually know that there is a gap. We don't have a good understanding of this gap characterization. I think that would be an interesting question. And with that, let me conclude the talk. Thank you so much for your attention. Yes?
I have a high-level question. I think this relates to what Alvin was asking about. So, like, let's say I'm a practitioner. I have an online optimization problem I want to solve. This seems to rely on me finding an stationary solution. Do you have anything to say about that? Or do you feel like that part is the practitioner's problem?
You mean how you can find the right example plan? Well, so typically the example plans that I'm referring to are coming from a simple mindset. So you have some feasibility constraint in your problem. Just imagine what would happen if they hold in expectation. And then that will give you hopefully some linear program or some convex program to solve. For that particular example, I mean, just imagine the vector of the selections in expectation should be feasible. And then you're trying to maximize maybe some rewards. So that will give you a linear program. And yes, so these linear programs usually can be solved easier because rather than searching over the space of algorithms, you're searching over the space of marginal probabilities. It's kind of like try to find the right probability that an omniscient benchmark would have allocated, say, resource I to user J, things like that. And yes, and then there will be some sampling procedure that should use independent sampling to create this example plan in an online fashion. And then online contention resolution is going to sit on top of that to give you a feasible algorithm that is not that far from the example. And yes, so the reason that people are excited about example, maybe I should have said at the beginning, is that we try to compete with omniscient benchmarks, the optimum offline benchmark, when you know the exact variables. And many times these example relaxations are set up in a way that omniscient benchmark will give you a feasible solution there. So they provide an upper bound. And if you compete with that, then you can compete with omniscient benchmark.
Questions? All right, thanks.
Yeah, thank you.